Hello everyone. Today we'll be having another example on retaining wall. The reference for this example is the book by Das and Sivakugan. So we are given a figure here, a cantilever wall having a given cross section. We need to calculate for the factors of safety with respect to overturning, sliding, and bearing capacity. So the cantilever wall will show as to the proportioning provided. Like we have the top of the wall having a width of 0.5 meters here, and we have the height of the retaining wall of 6 meters. We also have the height of the basement of 0.7 meters. We also have the base, which is given to be a total of, we have 2.6 here, 0.7 and 0.7. The base is about 4 meters. We are given an inclined backfill with an alpha equal to 10 degrees, and the soil backfill has the given properties. We have a unit weight of 18 kilonewton per cubic meter, an angle of friction of 30 degrees, and the cohesion of 0. So this is sandy soil. And this is on the active side of the wall. And we have here another soil on the passive side having a depth of 1.5 meters. And so we are also given that the depth of the water table is at least 4 meters below the base of the retaining wall. The soil on the other side of the wall here has a properties of 19 kilonewton per cubic meter for the unit weight, an angle of friction of 20, and a cohesion of 40 kilonewton per square meters. All right, with the height here from the top of the cantilever wall to the backfill is given to be 0.458 meters. So having all of this data with us, we are asked to determine the factor of safety against the overturning, sliding, and bearing capacity. So let us try to solve one by one by getting the necessary details or the other necessary information. And we can start by solving for the factor of safety against the overturning. But if you remember, to have an easy analysis, we can consider a tabulated solution uh, for us to easily see the following data or the given information, and for easily solving for the moment along usually the toe or here at the moment about C. Then the first thing that we need to do is to calculate the active force per unit length of the wall. Here we can consider the Rankine active force theory or the Coulomb force theory. But for this example, we'll be using the Rankine's theory. So the first thing that we need to do is to determine the active force per unit length of the wall. And let me write. Okay, if we are going back to our figure, the Rankine active force is this one, P sub A. And since we have an inclined backfill, we have to consider an inclined active force. If you remember, for the cantilever wall, you have to consider a line here, which is we call actually line AB. Here, this line. Okay. And this will be our force, PA. Okay, let me just enlarge it. And to determine that P sub A, we can use a formula. Our formula for the one we've learned from the lateral earth pressure, we have 1/2 of unit weight 1 here for the soil. We have H square and then the coefficient of active earth pressure, K sub A. But we have the total height is H1 plus H2 plus H3. So we can say that this is H prime. Let us consider this H prime and get the total H. We have H1 plus H2 plus H3. Okay. H1 is given to be 0.458. If that is not given, you can actually calculate that because you are given this triangle and you have here an alpha equals 10 degrees. Here, that's the angle here, and you have this distance or this dimension, which is 2.6 meters. H2 is given, which is 6 meters, and H3 is also given, which is 0.7 meters. And so the H prime here becomes 7.158 meters. All right, now to solve for K sub A, this is an active pressure, but notice that it is an inclined backfill. So if you remember, for an inclined backfill, we cannot use the formula for the horizontal backfill. We have a certain formula for the inclined backfill that can be found in our book. Okay. For Ka, for inclined backfill, let me write here. The formula would be cosine alpha multiplied by cosine alpha minus square root of cosine square alpha minus cosine square phi prime. Sorry. This is divided by cosine alpha plus square root of cosine square alpha minus cosine square phi prime. Or in the book, you can directly use the table 14.12. there is a relationship of alpha and angle of friction there. So from that table, we can say that, or we can get the value of K sub A, which is equivalent to 0.350, having an alpha equals 10 degrees and an angle of friction equals 30 degrees. So you can either use the formula or you can use the table. Now we already have H prime, we have Ka, the angle of friction is given, so we can solve now for the active force per unit length, which is equivalent to 1/2 of unit weight 1, which is here, that is 18, multiplied by H prime, which is 7.158 square, and Ka of 0.350. All right, so since we already have the active pressure or active force, we can now solve for the vertical component, P sub H, which is the horizontal component. Where's that? Let's see. This is P sub H. Sorry. And it's P sub H. And we also have here, okay, let me just change the color. We have here P sub V. So the horizontal component of the active pressure is P sub A multiplied by, this is 10 degrees, that is cosine 10 degrees. That is equal to, sorry, we haven't calculated the total value of P sub A. If we calculate that, that would be equal to 161.4 kilonewton per meter. So P sub A becomes, or P sub H rather becomes 161.4 multiplied by cosine of 10 degrees, and that will be equal to 28.03 kilonewton per cubic meter. Or rather, sorry, that is equal to 158.95 kilonewton per meter. Okay, then we calculate the vertical component, which is equal to P sub A sine of 10 degrees, and that would be 161.4 times sine of 10 degrees, and P sub V is equal to 28.03 kilonewton per meter. Okay, so let us just take note of the following values because we'll be needing that later on, here and this one. Okay, then if you remember, it is better to prepare a table showing all the data or information for every section for us to calculate the moment about point C here. This is our point C, and we will calculate the moment about point C. But before that, let us try to consider the sections. We'll be having the following forces that will act on the retaining wall. We have, of course, the weight of the wall here, here, and here. And we also have the weight of our backfill here, section 4 and section 5. And we also have the P sub V here, the P sub H. And of course, we also have P sub H here, or I mean P sub P, which is the passive. But we will neglect the passive pressure that is assumed to be neglected. So we're not considering the passive. That's for additional factor of safety because it will act as a resisting force to overturning. But in the meantime, it is assumed to be neglected. So let me just erase the forces to emphasize the forces that will resist in the overturning. We have the following forces. Let me put it in red. Okay. It is easier for us because we'll be needing the area. It is easier for us to consider sections. So we have several sections. We divided the cantilever wall into 3 sections. We have section 1 here, which is rectangular. We have section 2 here, which is triangular. And we'll have section 3 here. Let me just write here, which is section 3. And we also have the soil here and the soil backfill here. So we have 5 sections plus the vertical component of the active force. These are the forces that will resist the possible overturning. And the force that will tend to overturn the retaining wall is the horizontal component of our active force. So if we are going to have a table to show our solution, I'll be needing to move this downward. So we have several sections. Okay, let us right here. So we have like 5 sections plus the vertical component. So let's have 6. This is 1, 2, 3, 4, 5, and 6. Okay, let us say this is section number. We have 5, 1, 2, 3, 4, 5. And we have the piece of V section. Then we can write the area in square meter. And we have here the unit weight, This is in kilonewton per cubic meter. And we can write here the weight per unit length. And this is in kilonewton per cubic meter. We have here the moment, or let's say the moment arm first from point C, because we need the moment at C. This is in meter, and this is what we want. We need the moment in kilonewton meter per meter. By the way, because we need the factor of safety against overturning, let us write the formula here. This is equal to summation of moment that will cause resistance of the resistance to overturning divided by the summation of moment that will cause the overturning. And this should be greater than 2.0. Okay, so that's what we need. We need to get the sum of the moment that will cause the resisting and the overturning. Cause the resistance and the overturning. And so for the section 1, we have the concrete here, and we have a section equal to the height of this wall. Sorry. If we consider this here and here up to here, that would be 0.5 by 0.6. That is 0.5 by 0.6 meters. Oh, sorry, 6 meters. And then for section 2, we have a triangular area. The height is also 6 meters, but this distance would be, if this is 0.7, this is 0.7, and this is 0.5, so this is 0.2. So that's 1/2 of 0.2 by 6. So the area would be 1/2 of 0.2 by 6 meters. And then our third section is the base of the wall with a height of 0.7 here, multiplied by the width of the base, which is 4 meters. So we have 4 by 0.7. The area for section 4 is this one. So the height is 6 meters, and we have a width of 2.6 meters. So we have width of 2.6 by 6 meters. Then the fifth section is this triangle for the soil. We have 2.6 by 0.458. And that is triangle, so we have 1/2 of 2.6. Sorry. So we have 1/2 by 2.6 by 0.458. All right. The unit weight are also given for sections 1, 2, 3. Since this is a concrete, and it would be the given unit weight is 23.58. This is in kilonewton per cubic meter. So we can just write here 23.58. We also have 23.58 here and 23.58. And 4 and 5th section would be 18 and 18. Okay, let me check this one. This is the weight per unit length, so it should be meter only. Meter. Now let's multiply the area by the unit weight. So we can get the unit weight per length. Multiplying zero point 0.5 by 6 by 23.58 will give us 70.74. Or can actually calculate the area, total area. So maybe we'll be needing that later. But there's no more space. Let me just give you the value. The area here is equal to 3. Here we have 0.6. Let us just erase it first so we can write the total area. And we have here 2.8. And here we have 15.6. And here we have 0.595. So again, I erased it again, sorry. Again, for the unit weight of concrete, this is, let me just write here, 23.58. This is also 23.58. This is 23.58. This is 18. And let me write here 18 as the unit weight. So if we multiply 3 by 23.58, it will give us 70.74. If we multiply 0.6 by 23.58, it will give us 14.15. And if we multiply 2.8 by 23.58, it will give us 66.02. 15.6 times 18, it will give us 280.8. And 0.59 times 18, it will give us 10.71. So our piece of V is already known, which is 28.03. So this is our piece of V, 28.03. Now, if you want the moment arm from point C, for our section 1, the moment arm would be, let me consider this, from the centroid of the width, which is 0.5, so that is 0.25. Here is the moment arm from point C. That is 0.7 plus 0.2, that's 0.9, plus 0.25, so that will give us 1.15. So the moment arm is 1.15 for section A, or 1 rather. For section 2, we have here, which is the centroid of the triangle here, and the base is 0.2. And we need this distance. That's 0.2 times 2/3 plus 0.7. 2/3 of 0.2 plus 0.7. That would give us 0.833. This is 0.833. And the moment arm of section 3 will be base divided by 2. So that is simply equal to 2. 4/2. And then For section 4, we have here this distance. This is 2.6. The half of 2.6 is 1.3. 1.3. So the distance would be 1.3 plus zero point 0.7 plus zero point 0.7. So 1.4 plus 1.3 is 2.7. And the distance of our section 5 here from C, that would be 1.3 plus 2/3 of 2.6. And that will give us a distance of 3.13. While the distance of our piece of V here is, of course, 4 meters. There you go. Okay, so what we need here are the moments now. We have to multiply the weight per unit length by its moment arm. So we can get here 70.74 times 1.15. This will give us 81.35. 14.15 times 0.833. This will give us 11.79. 66.02 times 2. It will have 132.04. Then we have 280 times 2.7. This will give us 758.16. And this will also give us 33.12. And 28.03 times 4 will give us 112.12. Okay, so the next thing we need to do is to get the sum of the moment resisting. But we can also get moment, the sum of the forces, which will be used later on. So the total would be 470.45, while the sum of the moment resisting is equal to 112.98. Oh, sorry, 1, let me correct it. This is equal to 1128.98. Yeah, that is in kilonewton meter per meter. Okay, so this now is the total moment resisting. And for the overturning moment, which will be coming from only coming from the horizontal component of our active pressure, then we have P sub H, and the distance would be 1/3 of, okay, this is located half of 6 plus, all right, we can consider the total height, which is 7 point, where is that? 7.158. So the total force is acting upon the whole length here, divided by 3. So this is H prime divided by 3. So we have H is 158.95 multiplied by H, which is 7.158. divided by 3. And the sum of the moment that will cause overturning is equal to 379.25 kilonewton meter per meter. Okay, let me just write the answer here. The factor of safety against overturning is equal to 1128.98 divided by 379.25, and this will give us 2.98, which is obviously greater than 2. Therefore it is safe against overturning. Next, we would like to determine the factor of safety against sliding at the base of the toe. And from this figure, we can say that the sliding will be caused by the horizontal component, which is P sub H, while the resisting force against sliding will be the shear here at the base of the retaining structure, and of course the passive pressure here. And formula has been derived to calculate the factor of safety against sliding, and that is equivalent to the sum of the pressure multiplied by tangent of K sub 1, P sub 1 plus B, K sub 2, C sub 2 plus P sub B divided by P sub H, or this is P sub A, cosine of alpha. Okay, from this equation, we can calculate P sub B. We have the summation of the forces vertical as previously calculated. We have the angle of friction here, which is 20. And that is the angle of friction. We have C sub 2, or the cohesion, which is 40. We have the base, which is 4, given to be 4 meters. And K sub 1 and K sub 2 are constant, and that could be in the range of 1/2 to 2/3. So for this example, it is assumed to be 2/3. So alpha is given and PA, and it's actually equal to our pH earlier. So we also have this value. Then we can just solve first for P sub B before we plug in the values. And from the pressure distribution for this passive earth pressure coefficient, so it's like we have here, and we have cohesion. We already have a formula derived for that, which is equal to 1/2 K sub P gamma sub 2 D square plus 2 C sub 2 square root of K sub P and multiplied by D. Okay, so we solve first for K sub P because we don't have, we can use either formula, but let's just use now tangent square 45 plus P sub 2 over 2, and that would be equal to tangent square 45 plus the angle of friction is 20. So this is 20 over 2. And our K sub B here becomes 2.04. The depth of the depth is equal to 1.5. The depth of the soil on the passive side, the backfill at the passive side. So we can just solve now for P sub B. We have 1/2 of 2.04. The angle of friction is 19. Here we have D. We have 1.5. That is just right. D is equal to 1.5 meters. This is square plus 2. C is 40 multiplied by K sub B of 2.04. Now this is a square root. Multiplied by 1.5. From here, P sub B is calculated as 215 kilonewton per meter. And I think all the data are available. So we can now solve for the factor of safety against sliding. And the summation of B is found here, which is this value, 470.45. We have here 470.45. This is to be multiplied by tangent of K is equal to 2/3. Phi sub 1 is 20 plus 4, which is the width of the wall. K sub 2 is also 2/3. And the cohesion is 40 plus P sub B of 215. We have to divide all of this by our value, P sub H, and that is equivalent to, where's our P sub H here? 158.95. So this is 158.95. Okay. So the factor of safety against sliding is calculated as 2.73. And we have a limiting value of 1.5 for it to be safe. And it is greater than 1.5, therefore it is safe. Lastly, we would want to determine the factor of safety against the bearing capacity failure. And the formula that we have for the bearing capacity failure is factor of safety against the bearing capacity is equal to Q sub U over Q max, or the maximum pressure at the base of the retaining wall. We remember that Q max is normally found at the base of the toe. Here, this is our Q max, which is the pressure at the toe, and the minimum pressure is normally found here at the heel. So this is the minimum for Q ng heel. For the ultimate bearing capacity, that is obtained from the formula that we've learned from shallow foundation, which is C and C plus, or rather, C and C F sub CD. These are the F sub Ci plus Q and Q, F sub QD multiplied by F sub QI. That's plus 1/2 of gamma 2 B prime and gamma F gamma D multiplied by F gamma inclination. Okay, but anyway, the Q sub U is given to us already, which is equivalent to 552.8 kilonewton per square meter. And so we just need to have Q sub max for us to calculate the factor of safety. Now, the resultant force for the bearing capacity can be found anywhere along the base. Let us say this is our R, and we need to find the eccentricity of this from the center of the base. If this is B over 2, this is B over 2. From here, we need to get the eccentricity. And E is already or can be calculated using the equation B over 2 minus summation of the resisting moment about C and the overturning moment divided by the vertical forces summation. And if you notice, we already have these values. B is the width of the foundation, which is equivalent to 4. The sum of the moment resisting and overturning and the summation of forces, for pressure vertical, is already calculated in the previous question. So we can now directly solve for E. This is B, which is equivalent to 4 divided by 2. The sum of the forces resisting, I'll go back to our here. Here we have it. We have the sum of the moment resisting, which is 1128, and the overturning is 379.25, and the forces vertical is the 470.45, or the total pressure vertical. So we just plug in these values here in our example. So we have 1128.98 minus 379.25 divided by the sum of the vertical pressure, 470.45. So from here we can calculate for our B, or E rather, which is equal to 0.406 meters. And this value will have to be checked against the B over 6. Our B over 6 is equivalent to 4 over 6, which is equivalent to 0.666 meters. And obviously, E is less than B over 6 here. So in that case, we can go on with the analysis, because if E is greater than B over 6, there is a negative Q mean, which means that there is a tensile stress at the end of the heel section, which is not desirable because the tensile strength of the soil is very small. And so if we get E greater than B over 6, the design should be reproportions and we have to recalculate. But since it is less than, so we can go on with the procedure and calculate for the Q max, or we can actually calculate for the Q max and Q mean, so we can compare these values. The maximum pressure at the base, or the pressure at the toe is equivalent to our Q sub toe, which is summation of pressure vertical divided by the width of the base rather of the retaining wall multiplied by 1 plus 6E over B. And this is equivalent to 470.45 divided by the width, which is 4 multiplied by 1 plus 6. E is 0.406 divided by 4. So the Q max is equivalent to 189.2 kilonewton per square meter, while Q minimum is equal to Q at the heel, which has the same formula but opposite unit. This becomes minus 6E over B. So from here we can solve for, we have 470.45 all over 4, 1 minus 6 by 0.406 divided by 4. And we can get a Q minimum, let me just write here, which is equal to 45.99 kilonewton per square meter. Okay, obviously, what we need are these two values here and here. So we have to calculate for the factor of safety. Let me just write it here on the side. The factor of safety against the bearing capacity is equal to Q sub U, which is 552.8 divided by 189.2, and we get a value of 2.9. So the required factor of safety is 3, and this is about 2.9. So somehow it could be considered as safe, or if you want to redo your calculation to have a greater than 3 factor of safety, it's okay. But this, I can say it is still safe. Okay, so that is how you calculate the bearing capacity factor of safety.